There are three main layers of the Earth, and we're going to talk about those in detail right now. And the crust is the top layer. And there are two kinds of crust. There's oceanic crust and continental crust. In these boxes, you are going to write down some of these characteristics of each one of these crusts. So oceanic crust is, as you would expect, under the oceans. And so if you look down here at this diagram, we see in dark gray, we see the oceanic crust is underneath this water. And it's made of denser rocks. And that's going to have an effect we're going to talk about in a minute. And you can see that it's very thin. And over here we have continental crust. And as you would expect, it makes up the continents. It's made of less dense rocks. Okay, so let's compare what happens if you're made of less dense rocks versus if you're made of more dense rocks. In this picture, I can see that oceanic crust is colliding with this continental crust. They're headed towards each other, as you can see by these white arrows here. Well, when you're more dense, when you run into something that's less dense, you are going to sink. And so the result is that when oceanic crust and continental crust collide, the oceanic crust sinks down beneath the continental crust. And you can also see that the continental crust would be thickest where there are mountain ranges. Now, this idea of ocean crust being more dense and going underneath continental crust when they collide, that's referred to as subduction, and we're going to be talking about that in greater detail in the future. The mantle, we've studied the mantle before in past grades, and it was just, there's the mantle. But now we're going to learn how the mantle is actually composed of three layers within that. There's the lithosphere, the asthenosphere, and the lower mantle. Now, the lithosphere, it contains the crust and the upper part of the mantle. So if I go back to this slide here, so they just called this lithosphere, but really what this is the uppermost part of the mantle, which they made light gray. But the lithosphere also includes this crust sitting on top of it. So in this picture, they used light tan for continental crust, dark brown for oceanic crust, and then this tan color right here represents the upper part of the mantle that makes up the lithosphere. So you can see the upper part of the mantle, which is tan, plus any crust sitting on top of it, that is referred to as the lithosphere. Now, this layer is very rigid, and it's so rigid that we are going to learn that it's actually been broken up, and those broken pieces are called plates. Now, the asthenosphere is underneath the lithosphere. The asthenosphere is the middle part of the mantle. And it's still middle, it's like the middle upward part. So they're still calling it the upper mantle here. But you can see here's the uppermost part of the upper mantle. And then down here we have what's underneath that. And then you can see these little brackets are telling you that this is called the asthenosphere. And this layer is very soft. So I went back a slide. There we go. It's very soft. It's weak. It's so soft that sometimes people want to call it a liquid. But they decided that the asthenosphere is not a liquid. It can actually flow very slowly, but it's still considered a solid. One thing that they compare it to is taffy. Taffy is definitely a solid, but taffy you can pull it and it can stretch, and the heat can actually mold and change its shape a little bit. And then the lower mantle, which we don't have in this part of the picture, they have it over here. Here's the crust, the upper mantle. This upper mantle, the top part, would make up the lithosphere with the crust. This part here would be the asthenosphere. And then we have the lower mantle right here. And that's really hard rock, but it's very, very hot because as you go towards the center of the Earth, it gets warmer. Now, last we have the cores. The cores are large spheres of metal that are made of iron and nickel, primarily iron. Sometimes people will just say the core is made out of iron, but technically it's mostly iron and some nickel. And it's made, the outer core and the inner core, while they're both made of the same thing, they're slightly different. The outer core is made of liquid metal. So it's so hot in the outer core that iron and nickel are completely melted. In the inner core, it's made of solid metal. Now, that's kind of weird because we know as we go towards the center of the Earth, it gets hotter and hotter. So the inner core is the hottest layer, and the metal is solid. The outer core, while it is very hot, is not as hot as the inner core, and yet it's hot enough to melt it and make it liquid. So why is that? So in the inner core, it's hot enough to actually melt the iron and nickel, but there's so much pressure pushing in that it keeps it a solid. If I come back to this picture here, so I go down, it gets hotter, it gets hotter. I get to the outer core, we have iron and nickel here, and it's so hot that it becomes melted. The inner core, the iron and nickel are even hotter. The only thing preventing them from melting is the fact that you have all these other layers of Earth pushing down because gravity's pulling everything to the center, and all that pressure prevents these particles from being able to flow around. And instead, they're held in this like rigid structure, which is what makes them a solid. Now, just a reminder, at any time, pause the video in order to be able to get your notes. Here, I want to show you one thing about the outer core. When you have a metal that is liquid, and you have temperature differences, you're going to have a convection current. So I'm going to show you a convection current right here. We see we have a Bunsen burner, we have a liquid, in this case water, and we can see that down here near the Bunsen burner, the liquid gets hot. Well, hot fluids rise, just like you've learned in studying weather. Hot air rises, hot liquids rise. And then when they get farther away from the heat source, they cool off. And then when they cool off, they become more dense. So then they sink. And then they get closer to the heat source and they get hot and they get less dense. So they go up. And this is called a convection current. And so it's believed that in the outer core, and this is a picture of the outer core and the inner core, they show these convection currents with these little twirly blue lines here. That there are all these convection currents, that the liquid that's closer to the inner core gets hot and it rises, and then it gets farther away from the inner core and it cools and it sinks, and then it gets closer to the inner core and it gets hot and it rises. And this process just repeats itself over and over again. Well, when you have a metal moving around like that, you can generate a magnetic field. And this blue circle is supposed to represent the Earth. And it's like, you could think that we have a magnet inside, except it's not an actual magnet. It's actually this metal moving around, generating a magnetic field. And so the Earth has a magnetic field because of these convection currents that are going on in the outer core. Now, we love this magnetic field because look at what it does for us. In this picture, you'll see the sun. This represents the solar wind of the sun. Now, a solar wind is all these charged particles that kind of blow out from the sun. And this very, very tiny little thing there is the Earth. And all these blue lines here represent our magnetic field. And so you can see our magnetic field is kind of acting like this shield, protecting us from the sun's solar wind. So what would happen if we didn't have our magnetic field? Well, our magnetic field is responsible for deflecting most of the solar wind, whose charged particles would completely strip away our ozone layer. And if you recall, the ozone layer is a layer that protects us from the sun's ultraviolet radiation. And so without this magnetic field, our ozone layer would go away and we would be very susceptible and just at the mercy of sun's radiation.